Welcome to a lesson on absolute and conditional convergence of an infinite series. If a given series converges and the absolute value of the given series converges, then the given series is absolutely convergent. However, if the given series converges but the absolute value of the given series diverges, then the series is conditionally convergent. So to determine absolute versus conditional convergence, we're going to take a look at the given series as well as the absolute value of the given series. Let's go ahead and give it a try. The given series is an alternating series, so we'll start by applying the alternating series test. So looking at this infinite series, we know that a sub n would be the non-alternating part of this formula, so a sub n would be 1 over n plus 2. So using the alternating series test, we'll start by taking the limit of this to make sure that it's equal to 0. Our numerator is fixed, our denominator is increasing without bound, so this limit does equal 0. And now we need to make sure that a sub n plus 1 is always less than or equal to a sub n. To determine a sub n plus 1, we'll replace n with n plus 1. So we'd have 1 over n plus 1 plus 2, which would be n plus 3, less than or equal to a sub n, which is 1 over n plus 2. Well, these denominators will always be larger than these denominators here, and therefore this fraction will always be less than or equal to this fraction here. So both conditions of the alternating series test have been met. So this given series is convergent. But now I want to determine if this series is absolutely convergent or conditionally convergent. So now we'll take a look at the summation of the absolute value of this. So we'll just have the summation of 1 over n plus 2. Let's go ahead and do that on the next screen. If this series converges, then the original series is absolutely convergent. And if this series diverges, then the original series is conditionally convergent. To determine if this series is convergent or divergent, let's use the integral test. So we'll let f of x equal 1 over x plus 2. So if we apply the integral test, then if we take the integral from 1 to infinity of 1 over x plus 2 with respect to x, so if this improper integral converges, so does the series. If it diverges, so does the series. So this will be equal to the limit as b approaches infinity of the integral from 1 to b of 1 over x plus 2 with respect to x. If we let u equal x plus 2, then du would just equal dx. So the antiderivative of 1 over u would just be natural log u. So in this case we'd have natural log x plus 2. But this is a definite integral. So we're going to have the limit as b approaches infinity of natural log b plus 2 minus natural log of 1 plus 2, or natural log 3. Well, as b approaches infinity, so does the natural log of b plus 2. So we can state now that since the summation of 1 over n plus 2 diverges by the integral test, the original alternating series is conditionally convergent. Let's go back to the previous screen just for a moment. We have the original series, which by the alternating series test converged. Then we consider the absolute value of this infinite series, as we see here. And since it diverged, that tells us that the original series is conditionally convergent, not absolutely convergent. Let's take a look at another one. Notice the given series is alternating, so we'll apply the alternating series test. So a sub n is going to equal 1 over n times the cube root of n, which is the same as n to the 1/3. So let's go ahead and rewrite this as 1 over n to the 4/3 power. Now we'll take the limit of a sub n, and this limit does equal 0. So now we just need to check to make sure that a sub n plus 1 is less than or equal to a sub n. Well, a sub n plus 1 would be n plus 1 raised to the 4/3 power, and a sub n is just 1 over n to the 4/3. Notice these fractions here would have a larger denominator than these fractions here, and therefore these fractions will always be less than or equal to these fractions here. So we have met both conditions from the alternating series test, so this given alternating series does converge. But we want to know if it's conditionally convergent or absolutely convergent. So now we'll consider the summation of 1 over n times the cubed of n. Which, as we said before, is the same as 1 over n to the 4/3 power. To determine if this series converges, we can apply the P-series test. By the P-series test, with P equal to 4/3, which is greater than 1, this series converges. So since the original alternating series converged, and the absolute value of the alternating series also converges, we can state that the original alternating series is not only convergent, but it's absolutely convergent. I think we have time for one more. Let's start by applying the alternating series test, where a sub n is going to equal 5n divided by 9n minus 2. If we take the limit of a sub n as n approaches infinity, because the degree of the numerator and denominator are the same, this limit is equal to the ratio of the leading coefficients, or 5/9. So this alternating series fails the nth term divergent test and therefore is divergent. And I think we're out of time. Thank you for watching.